Okay, so let's move on to covalent compounds. Covalent compounds is when you have a nonmetal attached to a nonmetal. We're only going to focus on two nonmetals bonding together and not more than that. But they have a completely different naming style, different types of Lewis structure that is created. So we're going to go through that right now. So let's first start with the naming. So with naming, okay, the first element is going to keep its name. Okay, so you don't change the first element's name, but the second element that is in the compound, you're going to change it to have an IDE ending. Okay, we're also going to use Greek prefixes to identify the number of atoms. Okay, so let's go over the Greek prefixes. You know some of them, but the first one is going to be mono, 2 is going to be di, 3 is tri. You should know this one, like tricycle, triangle. 4 is really difficult because a lot of people want to say like quad, but the Greek word for 4 is tetra. Think about the game Tetris. Okay, Tetris is a bunch of blocks that are made out of 4 squares. Okay, that's why it's tetra. Think Tetris. Okay, 5 you should know, like what is a shape that has 5 sides? Penta. 6-sided shape, hexa, like hexagon, pentagon. 7 is hard because a lot of people want to write septa. I'm not quite sure, but it's hepta. So hexa, hepta. 8 like octagon, octa. If you want MMA sports. Right? Penta, pentagon, right? 9 is nana, so you probably haven't heard that one. And then deca is number 10, like decathlon, every decade is 10 years. So those are the Greek prefixes. Now, out of these 10, there's one that's really special, and that's the number 1. You never write mono on if it's on the first word, okay? So we're gonna make a little note right here and put second, because you only write mono on the second element only if it needs it, okay? So for example, here you have 2 nitrogens, right? So you have to write di to represent the number 2. Then the rule says the first element keeps its name. So N is nitrogen. So this is di-nitrogen, okay? And then here, if there's no number, remember a 1 is implied. So you would write mono. And then this is the element sulfur, but the second element has to have an IDE ending. So sulfur becomes sulfide, IDE ending, right? Very good. So let's see how's that different from this one right here. So here we only have 1 sulfur. But you do not write mono. Mono only belongs to the second element. So you just go ahead and write sulfur because the first element always keeps its name. So sulfur, and then you have a 3 here. So what's the prefix for 3? Tri, and then the element is oxygen, but you have to have an IDE ending. So it's gonna be trioxide. Very good. And that's how you do it. Okay, let's do a few more examples together. So going down here. All right, so here is dichlorine monoxide. So here we're going backwards. So you have to be familiar with your prefixes, right? So here's our prefix di, here's mono, here's hepta, carbon, and here's tetra, okay? So you see chlorine, which is Cl. Di is the number 2, so you put a 2 there, right? Mono, okay, is 1, right? Oxide, so you gotta be careful. It ended in an IDE ending, but so the root element is oxygen, right? So you put an O here. Remember that you do not have to put 1s here, right? But this is how it would look, monoxide. If we were writing it properly, it would just be like Cl2O like this without the 1. But that is dichlorine monoxide. Okay, so then here there is no prefix, right? There is none. That means there's exactly 1. So remember, we don't put mono in the first element. So when you write bromine, right, you could put a 1 here. And then you have heptafluoride. So it ended in "ide," but what is this root element? Fluor is fluorine. So you would write F for fluorine and then hepta. So if you forgot, you can go up and look up hepta. Hepta is here, it's 7. So you would write 7 down here. Okay, if you wanted to write it properly without the ones, it would be BrF7, right? Carbon tetrahydride. So once again, carbon doesn't have a prefix, so it's just one carbon. Here it ended in "ide." This is the prefix for hydrogen. Tetra, like the game Tetris, is a number 4. So it looks like this. If you wanted to write it without the ones, it would just be CH4, okay? Okay, so going back here, you have 5 and a 3 here. So 5 is penta, so I write the prefix. I'm gonna write the element. Br is bromine, so make sure you're spelling it correctly. 3 is tri, like triangle. And then fluorine, F, turns into fluoride, IDE ending. Okay, very good. So here we have 2 other numbers, a 2 and a 6. So I have to write di, and then S is sulfur. And then 6 is what shape? Hexagon, so hexa. So this one's really tricky. So you're like hydrogen, I need an IDE ending. So a lot of people end up writing like hydrogide or something, but the actual spelling is hydride, like this. Here we have a 3 and a 2. So this is tri, once again, like triangle. Si is silicon, trisilicon. 2 is di, di. And then I is iodine. So you have to change it to ide. So here you're like iodine becomes iodide. Okay, so then it's iodide. And you're like, oh, can you have double I's here? You can't. It looks really silly, but that's what it is, okay? Trisilicon diiodide. Very good. So there are more practice down here if you would like to do it, but we're going to move on to the next topic. Okay, so covalent Lewis structures are completely different. Why? Because electrons are going to be shared. This is our key word here. So they share electrons in order to receive a full octet, because that's what makes them stable, right? So with ionic compounds, you gave away electrons and some of them pick them up and they become positive and negative and they become attracted to each other. But covalent compounds are essentially like holding hands. They're gonna share electrons and hold each other's hands, okay? Now, all of the elements want a full octet except 2 elements. Hydrogen only wants 2 because it's gonna be closer to the noble gas helium. Well, I don't know why I put it that accent mark there. Helium, because helium only has 2 electrons total. So 2's good. Boron is weird. It's just one of the weird ones. It only wants 6 instead of 8. 6 makes it stable. So these are the only 2 exceptions you know. Okay, so don't be a high boron. Remember hydrogen and boron, that they have exceptions. Everybody wants 8 except for these 2 elements. Okay, so remember, covalent compounds are created when it's 2 nonmetals are being bound together. So let's go ahead and draw Lewis structures, okay? Not that you're gonna be drawing them from hand from scratch, but it's a good idea to know exactly how they come about, okay? So bromine is Br, right? And then if you look on the periodic table, bromine over here, it has 7 valence electrons, okay? So I am gonna draw bromine with 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I have 2 of these that I need to consider, okay? So I am going to draw them one more time. So bromine and another bromine. Okay, so the question is, what are these elements going to do so that they both can achieve 8? Because right now they both have 7. So this one has 7 and this one has 7, right? 7 valence electrons, 7 valence electrons, right? So you see here that these electrons come in a pair, right? They have a friend, they have a buddy. These electrons come in a pair, and also these electrons come in a pair. So all of these pair of electrons have a friend, okay? Now we have some solo electrons. This electron is all by itself, and this electron is all by itself. So what are we going to do? We're going to hold hands. And if we link them together, then you can share electrons, and then they can become friends, right? And then they become linked together. So if I were to redraw this, okay, so you can see it, you basically have a bromine, right, with 2 electrons here, 2 electrons here, 2 electrons here, and another bromine with 2 electrons, 2 electrons, 2 electrons. And basically this electron is going to be shared with this electron, okay? And so what you're essentially doing is having bromine share these 2 electrons so that they both have 8. So for example, there's 2, 4, 6, 8 electrons because these 2 are being shared, right? So they belong to both elements. And then you have 2 for this bromine, 2 for this bromine, 2 for this bromine, and also these 2 now belong to bromine, right? Ooh, that color is really dark. So you're essentially allowing them to be shared, right? So here, 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 and then here. They belong to both, right? Which is why, hey, see, blue and yellow make green here. So they're shared with both. So then both bromines have 8. Everybody's stable, everybody's happy, okay? So just know that the way I drew it up here, this is like scratch work. This is what it officially looks like, okay? I'll draw it in my nice orange box here, okay? So then, next elements to consider, okay, is HCl. So here I'm just gonna say what column they're in. So hydrogen, it has 1 valence electron, chlorine has 7. So I'm going to just put a 1 and a 7 here, and then I'm going to draw it over here. So hydrogen has 1 valence electron. Chlorine has 7. 1, 2, 3, 4, 5. Whoops. So if I, sorry, if I were to like draw it properly, it goes 1 on each side, 1, 2, 3, 4, and then 5, 6, 7. The reason why you draw 1 on each side is that so that you can properly see exactly which electrons have friends or buddies and which one does not. So you can see here that this electron is all by itself. This electron is all by itself, so they're going to link together. If we were to redraw this linked together, it would be like an H linked and shared with a chlorine. So now everybody is stable and happy, right? This chlorine gets 2, 4, 6, right? And 8, right? And then hydrogen, both of these electrons are shared, right? And remember, hydrogen only wants 2, so it's completely stable. So this is what it looks like here. Okay, so let's do a few more examples. BF3, so boron tetra, or sorry, not tetra, boron trifluoride. So boron is here, column 3, fluorine is here, column 7. So I'm just gonna write 3 and 7. So it says I have 1 boron and 3 fluorines. So I'm gonna draw 1 boron, 1, 2, 3, and 3 fluorines. 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So we can see here, there's 2 there, 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 and 2 there. So there's a lot of individual. There's an individual here, 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 and here. Okay, so you want all of them to connect because it creates one big covalent compound, right? So you can't just like connect these 2 and then you're like, I connected them. Well, what about boron and fluorine over here? So that can be connected there. You got to think of a way that all of them can be connected together. So hopefully you were thinking, yes, this can be connected here, this can be connected here, and this can be connected here, right? So this looks really messy. So if I were to like redraw it, right? That means that this boron is connected to a fluorine here. 1, 2, 3, 4, 5, 6, 7. This other boron is connected to a fluorine. 1, 2, 3, 4, 5, 6, and then 7, 8. And then this boron is connected to another fluorine. 1, 2, 3, 4, 5, 6, 7, 8, right? So that means everybody has 8. So if you look at boron here, good old boron has 2 electrons here, 2 electrons here, 2 electrons here. That's total 6. And remember, boron's weird. It only wants 6. And for fluorine, they get their 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8, right? So this is what the actual covalent structure looks like, right? Sorry, lost space there. All right, so carbon and hydrogen. Carbon is in the 4th column, hydrogen's in the 1st column. So I'm just gonna put a 4 and then a 1 here. So carbon is 1, 2, 3, 4. So you have to go 1 on each side, which is why we can see here that there's 4 solo dots. They all need a friend. And hydrogen has a solo dot. We have 4 of them, solo dot, solo dot, solo dot. So all of the dots here, none of them have friends. So they all need a buddy. So they need a friend. So all of these single electrons need a friend to pair up with. Now the question is, how do you get them all to pair up all together in one big happy family? So then here, you have to connect them all. So they get connected, they get connected, they get connected, and these get connected, okay? Ugly connections, so let's redraw it. So carbon is gonna get connected to a hydrogen, hydrogen. So I draw it like this so you know that basically that one of the electrons from carbon is being shared from one of the electrons of hydrogen. Technically, you don't actually see the circles. Like if I were to draw this again, you would normally see it like this, C with straight lines, H, 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 H. Okay, but I'm just trying to show you that this electron gets shared with this electron, but you don't have to draw the circles. Like they're all just straight lines. They just represent, there's electron here and electron here. Like if you're lazy, all the sciences are lazy, they just draw straight lines, okay? And this is what it looks like if you connect them all together, okay? All right, so now things can get a little bit more complicated, so I'm gonna do a couple more examples. Oxygen here is in the 6th column. So I'm just gonna write 6. So oxygen, remember it goes 1 on each side before you double up. That's 6. 1 on each side before you double up. Okay, so if you look here, these are already buddied up. So where are your single ones? You have a single one here, 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 and here. So what can you do? You can link them all up. Boop, boop. Okay, so you can have 2 or even 3 lines, okay, that link them all up together. So if I were to redraw this, this would be like an oxygen, and it's what we call double bonded to another oxygen. So 1, 2, 3, 4. 1, 2, 3, 4. So if you think about it, it's like 2, 4, and this is 6 electrons, 8 electrons, right? This is 2, 4, 6 electrons, 8 electrons. So each line represents 2 electrons. Remember that we're too lazy to draw the dots, but if you want to, like I like to draw the dots so that you know exactly that each line represents 2 electrons. So it's 2, 4, 6, 8, 2, 4, 6, 8, everyone's happy. So this is what it looks like here. Okay, our last example is nitrogen and iodine. So nitrogen has 5, iodine has 7. Woo, that's a lot of dots. All right, here we go. So, whoops, this is 5 and this is 7. Okay, so here we go. 1 on each side before I double up, that's 5. Okay, it says if you look at the name here, it tells you I need 3 of these I's, but I need 7 dots. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1 on each side before you double up. Okay, then you can see clearly where all your single dots are. Single dot, single dot, single dot, single dot, single dot, single dot, right? You gotta connect all of them together. So I'm gonna connect, 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 right? So then this end is gonna be attached. I'm gonna go off the page here to an iodine here, iodine there, another iodine here. It's important though that you don't leave it like this, okay? This iodine needs 8 total electrons. So if you leave it like this, it will get counted wrong. Why? Because you left off all the electrons. Like what happened to these electrons? These electrons are what we call unshared electrons. They're not being shared. It belongs to that element. So these electrons have to be drawn on your picture to show that they are not being shared. The lines are telling us that these electrons are being shared, but this iodine has 6 electrons that aren't shared. This iodine has 6 electrons that aren't shared. This iodine has electrons that aren't shared. And also a lot of people forget this nitrogen right here, but you can't forget there's 2 electrons here that nitrogen does not share, okay? Boop, don't forget about these. And that's how you draw covalent Lewis structures. Ta-da!